Hey everyone, so this is the solution video to Worksheet 10.2a. We're going to be working with sine and cosine in this section. So we're going to start off with number one. We're asked to consider theta equals 0 and determine the reference angle of an angle as long as it's not already a quadrant 1 angle or on some axis. Then based on that we can find the cosine and the sine of that particular angle. So for part A, we are asked to consider theta equals 0. So let's, in this case, get a just kind of visualize the angle here. So theta equals 0. We've got our x, and we've got our y-axis here. Theta equals 0 is just going to be an angle that has not rotated. So it's just sitting right there on the positive x-axis. So that's what we'll want to consider here, is that this particular angle lies on the positive x-axis. That's going to help us determine the value of the sine and the cosine in this case. So if we consider that, we know that the cosine of 0. Now, the idea being this, since it is on the x-axis, we know that the cosine will always be either positive or negative 1. Since it's on the positive side, it will definitely be positive 1. Whereas anytime an angle is on the x-axis, the sine will always be 0. Okay, so that's how we would do it for this one. For part B, we've got theta equals pi over 4. So let's sketch that angle and see where it lies. Might be helpful to consider, well, pi over 4, this is 45 degrees. If you're still trying to think about it in that manner. So 45 degrees is definitely going to be in the first quadrant, and it's going to be smack dab right in the middle. So there's our angle of 45 degrees. Now, since it's in the first quadrant, we don't have to worry about a reference angle. We've got it right here. So now we're asked to find the sine and the cosine. So from this information, we should be able to do this. So we're asked to find the cosine of pi over 4 and the sine of pi over 4. Now, there are lots of different ways to do this and to think about this. The way that I'm going to do it in these videos is to consider a couple of triangles, just two that we need to keep in mind. And just in case you haven't talked about these in class, these are the ones that I'm going to use. So the two triangles we're going to use are a 45, 45, 90 right triangle. So if we have a right triangle where we've got 45 degrees, 45 degrees, this particular one, we're going to let the hypotenuse be 2 and these the sides be the square root of 2. Anytime we run into a reference angle of 45 degrees, we're going to sort of take this triangle and plop it into whichever quadrant we need to, and then use these sides based on whether or not the x or the y is positive or negative. Let's see how this would work in this case. So if we were to draw a reference triangle using the x-axis as one side, and our terminal side is the hypotenuse, we would have, you can see, a 45, 45, 90 right triangle, 45, 45. So this is our particular theta right here, that 45 degrees. Let's go ahead and we'll plot the information from this particular one that we just put over here, triangle, and using what we know about the sine and the cosine, we can figure out what the values are. So we know that the cosine is the ratio between the adjacent side of the angle and the hypotenuse. So in this case, the adjacent side is the square root of 2, and the hypotenuse is 2. For the sine of 45 degrees, it's the opposite. So the opposite side would be square root of 2. Hypotenuse would be 2. So we've got the square root of 2 divided by 2. This is going to be the method of solving these problems that we'll use in the videos. So let's try it again for this next one. So we've got theta equals pi over 3. So if we think about this as an angle in degrees, pi over 3 is the same as 60 degrees. So we are definitely dealing with the first quadrant angle, as we can see here. So let's go ahead and draw it. So we'll draw, here's our x-axis and our y-axis. Now we'll draw this angle right here. So this is our angle theta of pi over 3 or 60 degrees. I'm going to put that right there. Okay, and again, what we need to do is, given this, we need to find the cosine of pi over 3 and the sine of pi over 3. Now in this case we've got a 60-degree angle, so we can't use the triangle we used in part B. The other triangle that you'll need to know is a 30, 60, 90 right triangle. So it would look like this, and this is not perfectly to scale, but you get the idea. Let's say that this is a 60-degree angle. That means that this angle would have to be 30 degrees, and we've got 90. Again, let's let the hypotenuse just be 2. In this particular case, this tells us that the longer side, the side opposite the 60-degree angle, has to be the square root of 3, and the shorter side, the side opposite the 30-degree angle, is always going to be 1. So anytime we get a 60 or a 30-degree angle as a reference angle in these problems, we're going to use this, putting in the proper quadrant and making accommodations for positive or negative x's and y's, as we'll see. All right, so let's create this triangle and see how it follows through for this problem. So we draw a reference triangle. Again, one side is the x-axis, the other side is our terminal side, and then we've got the perpendicular that we draw. So first quadrant. So if we put the information from our right triangle, we've got a 2. This is square root of 3, and then this side is 1. So let's go to the cosine. We know that the cosine of pi over 3, which in this case we're going to use 60 degrees, is the adjacent side, which is 1, divided by the hypotenuse, which is 2. For the sine, it's the opposite side, which is the square root of 3, divided by the hypotenuse, which is 2. So what we'll see here is, as long as we can properly sketch this reference triangle that we have here, and remember these two special triangles, the 45, 45, 90, and the 60, 30, 90, we'll be able to answer all of these questions. Okay, let's look at part D. So pi over 2, that's 90 degrees, and we'll go ahead and we'll sketch this. Okay, now 90 degrees is going to have us rotate onto the y-axis. So this is on the positive y-axis. Okay, so we can't draw a triangle, so this is one that you're going to have to just kind of remember. When we need to find the sine and the cosine of angles that are on the axis, either the x-axis or the y-axis. We already did one that was on the positive x-axis. Now we've got one on the positive y-axis. Anytime you're on the y-axis, either side of the y-axis, the cosine is always going to be 0, and the sine will either be positive or negative 1. So in this case, since it's the positive y-axis, the sine of pi over 2 is going to be positive 1. So let's review that again real quick. So from part A, anytime you're on the x-axis, the sine will always be 0, and the cosine will either be positive or negative, depending on which side of the x-axis. Anytime that you're on the y-axis, your cosine will always be 0, and your sine will always be either positive or negative 1, depending on which side you're on. Okay, part E. So we've got 2 pi over 3, which if we wanted to, we could convert into degrees, and we know that that's going to be 120 degrees. And when we sketch this, we realize that we're actually going to be in the second quadrant. So when we rotate this, we're going to rotate 90, and then we're going to need to go another 30 degrees So we've got this angle going on right here. So we are in quadrant 2. Okay, so there's our angle. Now since we're in the second quadrant, we're going to need to find a reference angle. The reference angle is going to be this angle right here. Let's get another color up. All right, so we'll get orange. So the reference angle will be the acute angle that is formed between the terminal side and the x-axis. Now let's think about what the measure of this particular angle is. We know that when we started we had 120 degrees was the original. So what's left over? Well, we take 180 degrees, which is one full rotation from x-axis to x-axis, and then we back off. In this case, we're going to have to back off 60 degrees. So this angle right here is going to be 60. And that's going to be our reference angle. So with theta being 120 degrees, this tells us that our reference angle, which I'm just going to use theta sub r, has to be 60. Or pi over 3, however we want to think about it. All right, so let's see what this means, because the next thing that we've got to do is we've got to find the sine and the cosine here. So we've got to find the cosine of 2 pi over 3 and the sine of 2 pi over 3. Well, the process is going to be the same as we did for the other ones. First, let's draw our reference triangle. Now, in order to do this, we're going to have to draw a perpendicular from our terminal side to the x-axis. And we're going to look at this triangle that we formed here in the second quadrant. Now, since this angle is 60 degrees down here at the bottom, that means that this is going to have to be a 30-degree angle up top, which means that we've got another one of these 30, 60, 90 right triangles. So let's label this. Now, this is going to be 2. And we know that the longer side, the side opposite 60, is going to be the square root of 3. And the shorter side, opposite the 30-degree angle, is going to be 1. However, since we're in the second quadrant, we know that x's are negative and y's are positive. So that means that this side on the x-axis is going to be -1. So we've created our little reference triangle that we can now use this triangle to answer these questions about the cosine and the sine of 2 pi over 3. So again, let's think about this. So using this reference angle in this reference triangle, the cosine of 2 pi over 3 is the adjacent side, which is -1, divided by the hypotenuse, which is 2. And the sine is going to be the opposite side, which is the square root of 3, divided by the hypotenuse, which is 2. So the only difference between this and the previous problems is that since we were in a quadrant where the x was negative, we had to make a slight adjustment to our reference triangle. Let's try this again with part F. So we've got theta equals 3 pi over 4, which if we converted into degrees would be 135 degrees. So let's draw this. Again, 135 is going to put us in the second quadrant. So we draw our angle. It's going to be right in the middle there. So there's our rotation of 135 degrees. However, we're in the second quadrant. We're going to come up with a reference angle. So in quadrant 2, we know that our x's are negative and our y's are positive. And to get our reference angle, that's going to be this angle right there. So what is the measure of that angle? Well, the measure of the original angle was 135. So in order to get from there to 180, which is the other side of the x-axis, this angle right here would have to be 45 degrees. So again, we've got a 45-degree angle, which allows us to use our 45, 45, 90 right triangles. So let's make a note of our reference angle. So our reference angle, theta sub r, is going to be 45 degrees, or pi over 4. And this is what we're going to use to help us find the cosine of 3 pi over 4 and the sine of 3 pi over 4. Okay, so now we've got all that set up, we draw a reference triangle. So we're going to draw this down. We know that since this is a 45, 90-degree triangle we've just drawn here, 2, square root of 2, and then since it's on the x-axis in the second quadrant, it's going to be negative square root of 2. So here is our reference triangle. We will be using this angle as our reference angle to answer the questions about the sine and the cosine of 3 pi over 4. So for the cosine, it is the adjacent side minus square root of 2 divided by the hypotenuse, which is 2. And for the sine, it is the opposite side, the square root of 2 divided by the hypotenuse, 2. Okay, so these are definitely the type of problems that you're going to get comfortable doing. And we've got one more. We've got theta equals pi. Let's sketch this out to see what we're dealing with here. So pi is going to put us on the negative side of the x-axis. So this is the negative x-axis. All right, so let's think about this. This kind of goes back to our original one. So the cosine of pi, and then to find the sine of pi. So we're on the x-axis, which means that the sine is going to be 0 regardless. Now since we're on the negative side of the x-axis, the cosine is going to be negative 1. So we kind of compare that to our original problem. 0, again, it was on the x-axis, so the sine was 0 and the cosine was 1, but it's positive, that's why it's positive 1. And then here we're on the x-axis, the negative side. Sine is still 0, cosine is negative 1. Okay, so number 2. Suppose that alpha is a quadrant 2 angle where the sine of alpha is equal to 12/13. Find the cosine of alpha. A number of ways to approach this problem. So I'm just going to show one of them. I think it's, regardless how you want to approach this, it's good to sketch your angle just to kind of get a visual of what's going on here. So here's our x and our y-axis. And if we draw just any random second quadrant angle here, I'll just put it right here. This will be our angle alpha. And we're in the second quadrant, so we know that our x's are negative and our y's are positive. Okay, and what we're told is that the sine of alpha is equal to 12/13. Now, if we think about this in terms of triangles, we know that the sine is the opposite over the hypotenuse. So I'm going to draw a reference triangle here in the second quadrant. So the opposite side of our reference angle here is going to be the 12, and then the hypotenuse is going to be 13. And since we're in the second quadrant, the y is positive, and that's this height right here, which is 12. By the way, another way to think of the sine is the y-coordinate divided by the hypotenuse, which is sometimes called r as a radius. Now what we don't know is this side just yet, and that's going to be helpful because to find the cosine of alpha, we know that the cosine is defined as the adjacent side divided by the hypotenuse, or x divided by r. In this case, we don't know what the adjacent side is. We'll just call it x, but we do know that the hypotenuse is 13. So how do we get there? Well, what we're going to use is we're going to use the Pythagorean theorem to get us there. So we know that by the Pythagorean theorem, x squared plus 12 squared has to be equal to 13 squared. or x squared is going to have to equal 13 squared minus 12 squared, which tells us that x is going to be equal to, if we take the square root of both sides, plus or minus the square root of 169 minus 144. So if we take that through a little bit more, get a nice little long train of thought here, x is going to be equal to plus or minus the square root of 25, or x is equal to plus or minus 5. So which one is it? Is it plus or minus 5? Well, that's going to depend on what quadrant we're in. In this case, we're in quadrant 2. The x is going to be negative, so this tells us that x has to be equal to negative 5. And again, this is since alpha is in quadrant 2. Okay, so our x is equal to negative 5, so we're going to take this information and bring it up here and conclude that the cosine of alpha is going to be negative 5/13. And that's our solution there. Again, there's a lot of different ways to think about this, but this is just one way we could have done it. Okay, so number 3. So we're given a partially filled in triangle, and we're asked to find alpha, A, and B. Okay, so let's find alpha first. We don't have to, but it's probably the easiest one, so we'll get it out of the way. So we'll find alpha. So one of the things we can conclude about alpha is that it will be complementary to 33, because those two angles, 33 degrees and alpha, will have to sum to 90. So we know that alpha plus 33 degrees has to equal 90 degrees. So that means that alpha will have to be 90 degrees minus 33 degrees, which tells us that alpha will be equal to 57 degrees. So that was pretty straightforward, as long as we keep in mind the fact that what it means for two angles to be complementary. All right, next, just because it comes earlier in the alphabet, let's go ahead and find A. Again, there are a number of ways that we could find A. But one thing we want to consider is that we need to find A. We can't use the Pythagorean theorem yet because we have two unknown sides. So we're going to have to use information about these angles and the known sides to find A. So what's one way that we could connect side A with, say, angle 33 degrees? Well, we know that we could connect 33 degrees and side A using the cosine function. So we know that the cosine of any angle is the adjacent side divided by the hypotenuse. So the cosine of 33 degrees would have to be equal to A, the adjacent side, divided by the hypotenuse, 8. So we establish this relationship between known values and the unknown value that we're looking for. Again, we could have used 57 that we just found in the sine function, but this is just the way that I picked it, so that's what we'll do. So now we're going to solve this for A. So if we solve for A, we get A is equal to, we multiply 8 on both sides, and we get 8 times the cosine of 33 degrees. And to get an approximation, we'll use our calculators, making sure that you're in degree mode. So make sure that you're not in radian mode when you make this calculation. When you do make this calculation, if you've done it correctly, you should get that that A is approximately 6.71 units long. So that would be the length of side A. Again, you could have used, in this case, the sine of 57 degrees. This other angle we just found, 57. In this case, A is now the opposite side, and we know 8, so we'd still get A over 8. So A is going to be equal to 8 times the sine of 57 degrees, and you get the same thing. A is approximately 6.71. So you've got options here. Depends. All right, so lastly, let's go ahead and find B. Now finding B, now that we've got A and alpha, we've got lots of options here. One thing we could do is we could use the Pythagorean theorem. That's fine. We could use either of the 2 degrees, 57 or 33, or either of the 2 angles, rather. I'm just going to go ahead and use the sine of 33 degrees, because that's going to have to be equal to the opposite side of 33, which is B, divided by hypotenuse, which is 8. So B is going to be equal to 8 times the sine of 33 degrees, which if we type this into our calculator, we'll get B is approximately 4.36 units in length. Again, we could have used cosine of 57 degrees is equal to B over 8 and gotten the same result. So you got options. And again, you also could have used the fact that a squared plus b squared is going to be equal to 8 squared. And since we found A, we can solve for B. It'll work out either way. Okay, number 4. So we're going to suppose that the terminal side of some angle theta contains the point 3, -4. Find the sine and the cosine of that angle. All right, so let's sketch this scenario first. So if we get this set up, so here's our axes, here's our x and our y. Now the point x equals 3, and then y equals -4, means that this is our point right here. So a couple things to note. 3 is the x, 4 is the y. We are squarely in quadrant 4, where our x's are positive and our y's are negative. And if we were to draw this angle that goes through this point, this is one way that we could draw our angle theta. So what I would probably encourage you to do is to draw a reference triangle, much like we solved the problems in the first one. So if we draw our reference triangle, which again uses the acute angle formed by our terminal side and the x-axis, what we have here is a triangle. We know that the length of this side here is 3. We know that the length of this side here is -4. And then this is our unknown length r. Fortunately, we know that r squared is equal to x squared plus y squared via the Pythagorean theorem, which means that r squared is going to be equal to 3 squared plus -4 squared, which gives us r is equal to the square root plus or minus of 9 plus 16, or r is equal to plus or minus the square root of 25, or r is equal to plus or minus 5. Now here's the great thing about r, is that in this course we're only going to be dealing with positive r's, because the direction is always going to be positive. When you get into Calc 2 and you start talking about polar coordinates, you might have to worry about a positive or a negative r, but for this course we'll only use an r that's positive, so we can disregard the negative. All right, so we know that r is 5. Okay, so now we've got to find the sine and the cosine of this angle theta. So the cosine of theta and the sine of theta. Well, again, using our reference triangle, we've got all these sides. You can think of it as the cosine is the adjacent divided by the hypotenuse, and the sine is the opposite divided by the hypotenuse. Or another way that we've defined these functions in terms of x, y, and r. The cosine is always the x coordinate divided by the r, and the sine is the y divided by r. So however we want to think about it, we know that cosine, again, let me write this down here just to summarize. What we've got from this graph is that x is equal to 3, y is equal to -4, and r is equal to +5. So we can use this information up here that the cosine of theta will be 3/5, and the sine of theta will be -4/5. So that's one way that we could have approached this problem. Okay, and the last problem, number 5, is we want to find all real numbers x which satisfy cosine of x is equal to theta. Now, a little bit of a hint here. When it says real numbers x, we're talking about radians, because radians are just real numbers as opposed to degrees, which have that unit attached to it. So when you see that, we're talking radians. So what are we actually being asked to do here? Let's maybe think about this problem is asking. We want to find what angles give us the cosine is equal to 0. So for what angles is the cosine equal to 0? Well, if we sketch this out, one of the things that we talked about in problem 1 is that the cosine is always equal to 0 on the y-axis. So that's kind of the short answer to this problem is when theta puts us on the y-axis. So that's a very general conclusion here. So, if we're rotating theta, if we land here or here, that's going to give us the cosine is equal to 0. So how do we explain this? Well, let's start by finding the first solution. So we're going to start at 0, and we're going to start rotating and see when we hit solutions. So we start at 0, we rotate, and we hit our first solution. So we'll write this as x is equal to 90 degrees or pi over 2. Okay, so there's our first one. How far do we have to go till we hit our next solution? So we can keep going, and we're going to hit it at 3 pi over 2. Now, we're going to want to kind of identify the patterns here. So we went pi over 2 initially, then we went another pi. So we had our first solution here on the positive y-axis. The next one came when we went another 180 degrees or another pi. All right, well, when's the next one going to come? Well, we're going to go from there. We're going to rotate another pi. So we started at pi over 2 originally, and now we've gone 2 pi. And we can kind of keep this up, that we're going to hit it again at our first solution, pi over 2, and we go another pi. So I think it's pretty easy to see sort of the pattern that's going here. One other thing that we'll want to keep in mind is that we could have started on the, we found our first solution and then gone in the negative direction. So maybe we went pi over 2, and then we backed off, and we went in the negative direction, and then another pi in the negative direction, and then another pi in the negative direction. So some other solutions could have been x equals our initial solution minus pi, or x equals pi over 2 minus 2 pi, so on and so forth. So there's an infinite number of solutions to this seemingly simple equation here. So how do we sum it up without spending the rest of our lives writing all of the solutions? Well, we need to find a way to generalize it. So one way we could do this is we could say, so x is equal to pi over 2, which is our initial solution. So let's go ahead and write that. So that's our initial solution. And then we try to generalize the repeating pattern. So in this case, it's multiples of pi, either plus or minus. And the convention we use to write this is we say plus pi, which is how it repeats, our repeating pattern. And we're going to say this is pi times n, where n can be any integer. And we write that symbolically as n is an element of the set of all integers. So, in quotes, n is any integer. And that's what that bold Z is used for. And again, any integer, the integers would be things like, -2, -1, 0, 1, 2, 3, positive or negative whole numbers, including 0. So we could pick any integer, plug it in for n, and we get a multiple of pi that when we added or subtracted it to pi over 2, our initial solution, we would get a solution to our original equation, the cosine of x is equal to 0. All right, so we'll do a lot more with solving equations, but this is just sort of a basic one. And that does it for this. I think that's it, yeah. Yeah, so that'll do it for this worksheet, and I'll see you all in the next one.